Energy is at once an extremely useful and an extremely subtle concept. It took scientists centuries of studying heat and light and various mechanical processes before the basic definition of energy, the ability to do work, emerged. Once that concept was formulated, however, the systematic behavior of energy, the science of thermodynamics, advanced quite rapidly. The first great law of thermodynamics states, energy may change forms many times, but the total amount of energy in a closed system is constant. I have three objectives in this lecture. First, I want to explore the many ways that different kinds of energy transform one form into another. Then we're going to look at the first law of thermodynamics, the principle that energy can change form many, many times, but that the total amount of energy is constant. Finally, I'm going to tell you some of the consequences of the first law, including the concept of power, and a fascinating story about how the first law influenced ideas and debates regarding the origin and the evolution of the Earth. Let's begin by reviewing what we've learned already about energy. To understand energy, you first have to understand the formal concept of work, which is a force acting over a distance. Anytime an object accelerates, Newton says there's a force involved, and a force has to be acting over a distance. So according to Newton's first law of motion, energy is what allows accelerations, allows forces to operate in the first place. Energy is a very fundamental concept in this regard. And here we come to energy. Energy is the characteristic of a physical system that gives it the ability to exert that force over a distance. Armed with this definition, we can begin to catalog all the different kinds of energy in the natural world, all the different ways to exert a force over a distance. And just ask yourself how you might exert such a force. In the last lecture, we enumerated 6 of these different ways. You could throw something. That's kinetic energy of a moving object. You could store up potential energy, water behind a dam, for example, or a coiled spring, a battery, a magnet, something of that sort. You could generate a wave of sound, a wave in water, an earthquake. Then we also saw that heat is a form of energy, the form of energy associated with the kinetic energy of individual atoms. Light is a form of energy. It reaches us from the sun. It travels 186,000 miles per second. And finally, under special circumstances, mass itself is a form of energy. It has the ability to do work. That's quite a respectable inventory. So we're now ready to look at the systematic behavior of energy, the way it behaves in the universe, and look for the universal laws that govern energy. Let's begin, though, by thinking about symmetry. Symmetry is an amazingly important concept in science. Symmetry is the belief held by many, many scientists that there's some kind of balance, some kind of order in nature. Scientists of the past 4 centuries have held a firm belief that this universe possesses deep order. An extension of this conviction holds that matter is neither created nor destroyed. Under ordinary circumstances, atoms don't just disappear. They don't pop into existence. When a quantity like mass doesn't change, physicists refer to the situation as a conservation law. We say that in the closed system, matter is conserved. I'm introducing a new piece of jargon here, this idea of a closed system, and I want to make sure you get the understanding of a closed system. A closed system is like a box, and this whole concept of system is very important throughout science. It's like a box that contains matter and contains energy. And if it's a closed system, that box is closed. No matter flows in or out of the box, no energy flows in or out of the box. And we talk about systems like this in science all the time. We have the solar system. We have ecosystems. We have nervous systems, various systems. Sometimes they're partially open, sometimes they're closed, depending on how you want to define it. But this first law of thermodynamics relates to closed systems. An open system is one in which matter and energy can flow in and out. That would be true of most of the systems in your body, and also true of ecosystems, of course. That's a system in which sunlight can come in and matter does flow in and out. So these we'll be referring to systems quite often. Matter is conserved in a closed system. Matter is neither created or destroyed. And there are other various quantities that are conserved also in nature. We saw in lecture 5 that linear and angular momentum are conserved. So what about energy? We cataloged many different kinds of energy, and scientists asked the question, are these different kinds of energy also conserved? So how would you test something like that? How would you go about testing the conservation of energy? Well, you'd have to develop first a deep understanding of the different kinds of energy and the way that energy could change from one form into another. Since we have so many different forms, you'd have to weigh up all these different forms in your inventory of energy to see if energy is conserved. And that's exactly what scientists of the 19th century did. As a myriad of nature's many different ways of transforming energy, we can look at a few everyday events, sequence of events that we see all the time. One of the more dramatic ones is riding a roller coaster. This is a great way to think about transferring energy from one form to another. You start in the roller coaster, you're sitting still, and then all of a sudden an electric motor starts cranking and bringing the roller coaster higher and higher and higher up the hill, and you feel that rattling as you're going up the roller coaster. And you get more and more gravitational potential energy in a situation like that. You crest that very first hill, and then as you start going right over the top of the hill, then you start accelerating. You get more and more and more and more kinetic energy as you plunge down. And of course, you have less gravitational potential energy in the process. Some of the kinetic energy is converted into sound, the shrieking sound of the wheels. Some of it's converted into the heat of friction as the wheels hit the rails, as the axles grind against the chambers in the cars themselves. As the roller coaster goes up and down, energy constantly shifts back and forth between kinetic and gravitational types of energy. Ultimately, though, all the roller coaster's energy is dissipated as heat in the rails, heat of the brakes of the roller coaster, and so forth. You see other ways that energy transfers back and forth. You can do the same sort of thing if you drop an object. You can drop a ball. It has gravitational potential energy. It ends up on the table or on the floor. Sometimes the conversion of one form of energy to another is more efficient. A tennis ball bounces a little bit more because it has more elastic energy, and at various stages while it's bouncing it has more elastic potential energy. If you have a super ball, which has extremely high elastic modulus, it bounces much, much higher because there's a better, more efficient conversion of the kinetic energy into elastic potential energy, so it continues to bounce more and more. So we see different kinds of conversion: potential energy of the gravitational sort, the elastic sort, kinetic energy, and so forth, back and forth, converging over and over again. Another example is provided by the famous Newton's cradle, in which you see constant switching of motion of one sort into another. The energy seems to be constantly being transferred one place to another. Gradually, as these balls hit each other, they're also heating up slightly. You also have friction in the various parts of the machine, but that's another example of the transfer of energy from one form to another. Your car is a great example of the transfer of energy from one form to another. First thing you do is go to a gas station and fill up with gasoline. That's a form of chemical potential energy. That energy is converted to heat in your engine. It helps drive the engine. The heat is converted to kinetic energy. The kinetic energy then drives your car. It also can be converted to electrical energy in the generator in your car, which can power your radio. That can be turned into light energy, for example, when you turn on the lights, the headlights of your car, or sound energy if you turn on your radio. They're all different kinds of energy transfer going on constantly. Ultimately, you put your foot on the brake, the brakes get hot, and some of the energy that you've paid for at the gas pump goes into heating up your brakes. You might think also backwards from the gasoline. Gasoline is refined from crude oil. Crude oil is a kind of fossil fuel. It's pumped out of the ground, and it represents decayed plant matter that was deposited in Earth millions of years ago. That plant matter got its energy from the sun's radiant energy. So in a sense, you can convert all the way back from the motion of your car all the way back to sometime millions of years ago when the sun's energy shone down on the surface of the Earth and plants created plant matter, chemical potential energy from the sun's energy. The cycle goes on and on. One of the greatest challenges of modern technology is to find cheap and efficient ways of converting one kind of energy to another. Power plants convert chemical energy of coal, gravitational potential energy of water, sometimes the kinetic energy of wind, even nuclear energy of mass into producing electricity. And you want to do that as efficiently as possible because energy is expensive. Modern appliances are designed to produce kinetic energy and sound and light and heat from electricity. So that's another thing. We constantly are looking for ways of converting one form of energy into another. You can play this game. You can name almost any two forms of energy. You can list all those different forms of energy, all the different kinds of potential energy, gravity and chemical and magnetic and so forth. And you can list them in one column and also in a horizontal row, and you can match them up. How do you convert one kind of energy to another? You could play this game with your kids. You can actually write down on index cards all the different kinds of energy, shuffle the deck, and have your child grab two of them, and then try to say, how would you convert one kind of energy into the other? And almost always there's a technology that will do that. Sometimes they're pretty subtle, but there are technologies that we have now to convert one kind of energy into another. Okay, so energy can be converted from one form into another. There are lots of ways to do it. But the question then, is energy conserved? That's a very different question. Is the total amount of heat and potential energy and kinetic energy, is that constant through all these different transformations? And you have to then start quantifying energy. You can't just talk qualitatively about the amount of energy in a roller coaster. You have to quantify it. How much heat energy is contained in a pot of boiling water? How much gravitational potential energy is there in suspended weight? I mean, how much energy in joules? How can you calculate that? These calculations require a much more quantitative way of thinking and understanding energy. The first law of thermodynamics states categorically that the total amount of energy in a closed system is constant. No matter how many times it changes form, energy is neither created nor destroyed. That's the statement of the first law. Once that concept of energy began to be understood and all these different forms of energy began to be studied and quantified, then scientists suspected that this law must be true. But they weren't sure. They had to perform experiments of various sorts. But it's extremely difficult to demonstrate. It's difficult because it's so hard to devise an experiment within a perfectly closed system. Energy always tends to leak in or leak out of a system. The first universally convincing demonstration of this first law was an elegant experiment by the English physicist James Prescott Joule. He's honored today by the unit of energy, the joule, which we've talked about. Joule was born in 1818. He was the son of a wealthy Manchester brewer. He was home educated, had the best education possible with home tutors. He never held a professional job throughout his entire life. Joule's scientific work was supported by the family fortune, and he spent a great deal of his time and his energy trying to improve the efficiency of electric motors, which were just in their infancy when he began doing this research. In this effort, he was extremely concerned with accurate measurements of the conversion of energy from one form to another. For example, the conversion of electrical energy into mechanical work. In his most famous experiment, Joule agitated water with a paddle wheel. The paddle wheel was turned by clever linkages to two heavy weights, which were suspended by gears and pulleys. So as the weights descended, the paddle wheel turned. And he had an insulated chamber filled with water. What he did then was measure the temperature of the water as the paddle wheel agitated the water. And if you believed in the first law of thermodynamics, as the gravitational energy of the weights descending decreased, that energy had to be transferred into the heat of the water itself. He built very beautiful and accurate thermometers. He was able to measure differences in water temperature as you agitated the water with the paddle wheel. And he measured the direct conversion of 772 foot-pounds of mechanical energy, that is, the suspended weights, into 1 British thermal unit of heat energy. That's the energy required to raise the temperature of a pound of water by 1 degree. These are the archaic units that Joule used. So he actually saw the mechanical equivalent of heat in these experiments. This phenomenon also occurs in a waterfall. The higher the waterfall, the greater the heating of the water as it descends gravitationally. The water plunges down and crashes into the rocks below. The water actually heats up. There's a story, although it's probably apocryphal, that in 1847, Joule was on his honeymoon, and he and his young bride were hiking in the Swiss Alps, and they actually carried out this measurement. He carried thermometers with him. He stuck him in the stream above the waterfall and below the waterfall, and he supposedly measured the difference in temperature of the river at those two spots. Probably not true, but it makes a great story. It's the first law of thermodynamics that allows you to precisely calculate the mathematical change of energy from one form to another. I want you to consider just one example to give you a sense of the mathematical power of this law. Consider the conversion of gravitational potential energy to kinetic energy of a 40-meter tall roller coaster. So you have a roller coaster that's 40 meters tall, and how much kinetic energy can you actually get out of a roller coaster like this? Well, gravitational potential energy of an object of mass m raised to a height h, recall, is mass times the gravitational constant times h, mgh. So when you drop that potential energy is converted completely to kinetic energy, which is 1/2 mv squared. So we have the equation mgh equals 1/2 mv squared. Gravitational potential energy gets converted into kinetic energy. So what's the velocity, the maximum possible velocity of the roller coaster that's 40 meters tall? You can calculate that out. First thing you can do is you can multiply each side by 2 over m and simplify this equation. Then that tells you that v squared, the velocity squared, is equal to 2 times the acceleration due to gravity times the height. So substituting the numbers, height is 40 meters. The gravitational constant is 9.8 meters per second squared. So you can substitute that. V squared is 784 meters squared per second squared, taking the square root of both sides. The velocity, the maximum velocity, is 28 meters per second. That means the roller coaster's top speed is about 60 miles per hour. You can see this kind of energy transfer in all sorts of ways. Anytime you drop a weight, what you're doing is you're converting gravitational potential energy to the heat energy of the floor. The floor is now a little bit warmer than it was just a couple of seconds ago. It's hard to measure that change in temperature, but it's true. But there are other experiments of this sort you can do yourself with your kids. What I particularly like is if your kids are feeling very rambunctious, very energetic, and maybe it's a rainy day and you need to give them something to do that's energetic, give them a jar filled with sand. Let them measure the temperature of the sand with a thermometer. Seal up the jar, and then tell them they have to shake the jar until they raise the temperature by 1 degree. They're converting mechanical energy into heat. It's going to take them a while to do this, so they're going to use up some energy, but they'll keep opening the jar and measuring the temperature, and they'll have to seal it up and keep going. So it's a great activity, and it's a way of demonstrating the first law of thermodynamics just with a jar of sand. At this point, I want to introduce another common term, and that term is power. It has a very specific meaning in science. The first law of thermodynamics says nothing about how fast energy is transferred from one form to another. But your common sense tells you that this rate of energy release is very important. An example, a candle and a firecracker may transfer the same amount of chemical stored energy into heat and light. But they do it at very, very different rates when they're lit. The candle burns gradually, the firecracker explodes all at once. This rate of energy release is called power. And it's defined as energy divided by time. The standard unit of power is the watt, which equals 1 joule per second. This unit of power is named for the Scottish inventor James Watt. He lived from 1736 to 1819, and he made fundamental improvements in the steam engine. I want to tell you about James Watt. He's a great character in the history of technology. He was born in Greenock, Scotland, 1736. He was always mechanically adept, apparently, and at the age of 18, he went to London to study instrument making. Upon his return to Scotland, he was appointed mathematical instrument maker for the University of Glasgow. So here he was a technical person. He was a technician. He wasn't a scientist per se, but he made a fundamental important discovery. Watt began thinking about the design of steam engines when he was given the university's model of a primitive Newcomen-type steam engine to repair. So he's repairing this model, and he looked at it and said, boy, this isn't very efficient. In the Newcomen engine, there was a steam that drove a piston, but then a spray of cold water cooled the piston back down again. And so we're using cold water, and then you had to heat up the water again, and you had cold water again. This process resulted in a terrible waste of energy. It was a very inefficient kind of steam engine. Watt's great improvement was to devise a separate condenser that kept the water warm that you were boiling and reduced fuel consumption drastically. Watt, throughout his life, made many other improvements in the steam engine, and he continued studies in the steam engine until his death in 1819. Watt's remembered today primarily for his unit of power. We also commonly talk in electrical power supply as things like kilowatts. That's thousands of watts and so forth. So you hear about kilowatts and megawatts. So we honor Watt with the unit of power. But ironically, Watt himself introduced a very different unit for power. That was the horsepower. A horsepower is 550 foot-pounds per second. And the reason he did this is he was trying to sell steam engines. And in the early days, it was very difficult to convince mine owners to buy a steam engine to replace the horses. So he said, my engine is the equivalent of so many horses. And that's why he used this idea of the horsepower. The concept of power comes forcefully into play in sports. It's not just how strong you are, but it's how fast you can release your energy that determines who the winner is going to be in many sports. It's true for pitchers in baseball. It's true for home run hitters, power hitters. It's true for sprinters and shot putters. It's certainly true for boxers and running backs. It's that burst. It's the fast release of energy that gives you the most efficient use in many sports. We've defined power as energy divided by time. That is, P is equal to E divided by T. But this gives us a different way to calculate energy, because you can move this equation around and say energy is equal to power times time. So for example, this allows us to calculate the energy used by a 100-watt light bulb in 10 hours. Plugging into the equation, E equals power times time. Energy is 100 watts times 10 hours, or 1 kilowatt hour. That's what you pay for in your electric bill. And if you want to cut down on your electric bill, you have two choices. You can either turn off the lights, thus lowering the time that the light bulb is on, or you can use a light bulb of lower wattage, thus cutting down the amount of power that's consumed by that bulb. Energy is a pervasive theme in science, and every subdiscipline has to incorporate the concept of energy. Consequently, there have been a bewildering variety of energy units that have been introduced into science. You probably use half a dozen different energy units just in your day-to-day experience. And all of these units are interchangeable. They all stand for energy. They all can be converted to joules with appropriate scaling factors. For example, home energy bills in the United States, they commonly use kilowatt hours for electricity. They use therms for natural gas, gallons for heating oil. You use tons of coal. You use cords for wood. In other countries, they sell energy by the British thermal unit, the BTU. The English system employs the foot-pound or the horsepower hour, where that's about 2 million times larger. And you might think that scientists would get away from all this confusing units, that this would be something that really scientists would want nothing about, but it's just not true. Physicists, they use joules, but they also use ergs, which is 1/1,000,000th of a joule for everyday objects. They also use electron volts as an energy source or an energy term when dealing with atomic scale processes. These are all just different units for energy. Chemists then use a whole another set of units, reciprocal centimeters in some cases, calories. And actually, the calorie the chemists use is 1,000th of the calorie that you see in food substances, which is the energy contained in food. So the calorie in your food is actually the kilocalorie of the chemist. This gets really confusing at times. And there are many, many other odd energy units as well. The situation is just as bad, by the way, for units of force, for mass, for power, and so forth. Units are a big problem in science, and to systematize and unify them is something that we all like to see happen. If you ever have to do a calculation in a science class, by the way, one of the key things to do is to make sure you get your units straight and know your conversion factors. And you can often find such conversion tables in the backs of science textbooks. A really useful thing to have if you have to make those calculations. The first law of thermodynamics is more than just a useful statement about energy. To many scientists, it carries a very deep and profound significance about the underlying symmetry and the beauty of the natural order. Joule described the first law in the following poetic way. Let me read you a quote by Joule. Quote, "Nothing is destroyed, nothing is ever lost, but the entire machinery, complicated as it is, works smoothly and harmoniously. Everything may appear complicated in the apparent confusion and intricacy of an almost endless variety of causes, effects, conversions, and arrangements, yet is the most perfect regularity preserved, the whole being governed by the sovereign will of God." To Joule, the first law was nothing less than proof of the beneficence of the Creator. Others saw in the conservation of energy, in that natural law, something analogous to the immortality of the soul, and they made those connections. I want to end by telling you about one other British scientist, the great physicist William Thomson, who's also known as Lord Kelvin. And he certainly agreed with these sentiments about the beauty of the first law of thermodynamics. Kelvin was a towering figure in the Victorian era of science. He was born in Belfast, Ireland in 1824. At the time, his father was professor of mathematics at the Royal Academic Institution of Belfast, and so young William was home taught and got the most rigorous sort of education until the age of 10. That's when his father was offered the chair of mathematics at the University of Glasgow, and William, at the age of 10, entered the university. He was the top in his class in mathematics, in logic, and in classics. He published the first of some 660 scientific papers at the young age of 16. He went on to Cambridge for what was in effect graduate work in theoretical physics. While there, he was also on the rowing team. He helped found the Cambridge University Music Society, and that's still thriving today. After a brief time in Paris, he became professor of natural philosophy at Glasgow, and that was a position he held then for 53 years until his death in 1907. He was buried in Westminster Abbey near Newton and Darwin, and that should give you some sense of the esteem in which he was held. Well, Kelvin was drawn to the perfection of the first law of thermodynamics, the conservation of energy. He appreciated the economy, the symmetry of this law. On the other hand, Kelvin read with great distaste Darwin's theory of evolution, in which random variations and chance seem to play a central role. How could the creator of such magnificent order of the first law of thermodynamics then resort to chance and probabilities when it came to his highest creation, life? So Kelvin set out to use the first law of thermodynamics to destroy Darwin's idea. This is how he did it. He said every closed system, such as the Earth and the Sun, has a fixed budget of energy. For life to exist on the Earth, the Sun has to expend prodigious amounts of energy. And this is what Kelvin said, quote, "Within a finite period of time past, the Earth must have been, and within a finite period of time to come, the Earth must again be unfit for the habitation of man as at present constituted." In other words, you only had a fairly short span of time for humans to evolve and to live on the Earth. Making a few simple assumptions about all the different known energy sources in his time, the sun, the various kinds of fuels, gravitational collapse of the sun, and so forth, he decided that life on Earth must have been around for significantly less than 100 million years, perhaps only 10 million years. And this was much, much less than the hundreds of millions or perhaps billions of years required by Darwin and his theory of evolution. Kelvin was very wise to add when he said this, by the way, quote, "Unless sources of energy now unknown to us are prepared in the great storehouse of creation." So he kind of hedged his bets. It was Kelvin's reputation as a physicist, it was so great, and the laws of physics seemed to be so unshakable that his pronouncements were for half a century the principal hurdle, the major impediment to the acceptance of Darwin's theory of evolution. Darwin even referred to Kelvin and his opposition as, quote, "an odious specter," because he realized you couldn't fight the first law. This conflict was resolved in 1904 when Ernest Rutherford announced the discovery of a powerful new energy source, radioactivity. That's a manifestation of nuclear energy, and we're going to learn a lot more about that in lecture 27. Einstein's famous equation, E equals mc squared, appeared the following year. So clearly the sun and the earth had major energy sources that no one had recognized before, and that conflict between physics and biology was finally resolved. To summarize, this lecture is focused on the ways that energy can change from one form to another. We've seen that energy can change form many, many times, and that the rate of change of energy, or power, can vary widely. Nevertheless, the total amount of energy in a closed system is constant. Energy is neither created nor is it destroyed. The first great law of thermodynamics provides a glimpse of the order and the symmetry of the universe. The first law also provided a framework for investigating energy. But as we'll see in the next lecture, the first law is only half of the story.